Yeah. Hello, everyone. Today we have talk by Professor Valentina Zharkova. Talk about sunquakes and their consequences. Professor Valentina Zharkova is a professor in mathematics at Northumbria University. She graduated from National University of Kiev, Ukraine in 1975 and obtained bachelor and master's degrees from there. And then she is having impressive career with a lot of interesting findings and publications. So, Valentina, please go ahead. You have about 45 minutes for your talk and 10 to 15 minutes for questions.
Okay. So today we'll speak what sunquakes tell us about energy transport in solar flares, and with the help of the people who actively supporting and producing the images and model simulations and observations, Sergei Zharkov, Malcolm Druitt, and Sarah Matthews. Oh, it doesn't want, yes. So what are the sunquakes? This is the first sunquake which we discovered ages ago, I think now the 20 years ago, with Sasha Kosovichev, which is ripples which propagating from the location of solar flare. Ripples look like the ripples on the ocean, on the water, shown at the bottom of the screen, but it is only surface location of these ripples because they are not actually the surface waves, it's turned out. So how we detected it? It was using by a time distance diagram. So we discovered the reach, and on the axis X, it is the distance from the location of the sunquake. On the y-axis is the time, and here you see a nice reach showing that the wave, this ripple, propagates outside from the sun, from the flare, with the increasing velocity, because it has some kind of saturation. So what is in reality turned out that very often we don't have a single sunquake. We have sunquakes, a number of them, like in this flare 28th of October, which was basically showing, as you see, three sources here, ripples coming in each direction, they interfering with each other. So the picture will be much more complicated. Sometimes it is, you don't see even single ripples or the full ripple, the only part of them. So this is what keep happening. And no, I have problems with. In reality, what you discover when you look at the sources, actually we found 11 sources for this flare with the Doppler velocities, with the high Doppler velocity downwards. And these are these 1, 2, 3 in which we see sunquakes, but in these others, possibly they had sunquakes, we simply didn't see them. So how would this happen? How the sunquake detected with the time distance if we are lucky to have, for example, ripples. In this case, you have tried to see Doppler disturbances on the circle, remap Dopplergram with the center if 1 pixel where you assume the supposed impulse is deposited, then and apply frequency filter and Fourier transform signal with azimuthal angle theta, and plot Fourier coefficients for m0 for circular wave, m equal 1 for dipole wave. So basically what we did, we tried location 20 by 20 pixel and see where do we see time distance diagrams, which are reliably seen, and then we produce time distance with the reach. And hello? Someone is busy in my computer. Then use aggression power. This other technique which allows you to detect the disturbance when the reach cannot be detectable, where the increase of the ripples are not above the noise. But you still can see there is something organized in this location. So in this case, you use the green function and collect all the disturbances in some area. And what you bring, basically, you bring the back all the disturbances to the center where it been deposited. So you basically discover location of the impact. Recently, Mark Marshall and Sergei Kharkov, they developed the technique refractional holography. When you don't need to have the whole circle around it. You can choose only locations or Doppler disturbances only in particular angle. Grisha, I hear someone is breathing in my computer. I don't know why. Yeah, it's you. It's you. I hear you. Can you mute yourself? Thank you. So anyway, this is the thing which comes how sunquakes are detected. So this is the normal holography, and this is the one which McRae and Zharkov developed when you can have only data collected, let's say, from the quarter of the circle, and you still can see where this location is, where this disturbance comes from. So then what we did for the flare 28th of October, we discovered these nice three sources. So this is the source 1, which was the strongest one, started 1106, and it arrives to the 120 megameter side at about 45 minutes. Then you look at the source 2, which arrived slightly later, despite it started nearly simultaneously. And then source 3, which much more slower, arrives even later. So in each of those sources, we look at the pixels, and we discovered that it was a strong downward motion, Doppler motion, occurring during the 2 minutes when the sunquake occurred. So this is the downward motion of the source 1, of the source 4 and 1, and the source 3. So definitely it shows that when you have a sunquake, you have this downward motion, and it turns out that only quake with the downward motion above 2000 kilometers per second, 2000. Yeah, it can be detectable. Those which are lower, we don't see them as sunquakes, but we see them in the holographic image. So we did comparison and compared basically for quakes. The first ripple location where you first time see the reach when it starts, the momenta deposited, defined from the time distance diagram, and horizontal velocities, them at arrival to the 120 megameter cube. So here are the horizontal velocities in the last column. Here the time which was required for these particular ripples to arrive there. So you see the first one 49 minutes, another one 53, and the last third one 59. And obviously momenta which are required to deliver this particular reach. And when we compared for this particular flare with the simulation of hydrodynamics of atmosphere heated by electron beam with the parameters which are more or less suitable for this flare, we discovered that electron beam cannot produce this momentum by order of magnitude approximately. In some cases, only half order of magnitude. So it was something telling that basically what we have different, so sunquakes are not the same in every flare. They're quite different features, And this is the detection. So they are gamma ray emission shown by blue and hard X-ray emission by red. And it happened that the sources, definitely 1 and 3, were located where there was the gamma ray emission and not where the hard X-ray emission. So it was pointing out that the different wake can be produced by different mechanisms, but definitely it is associated with the downward motion at the high speed. So then what does it mean? The stronger acoustic response is associated possibly with magnetic field. So the particle precipitation should probably produce some disturbance to Doppler signals or Doppler shock. They form the Doppler shock in the atmosphere. And so it has to be related because it's the sun quakes normally associated with the particle hard X-ray emission. The timing is very close of start of the sun quake to the start of hard X-ray emission. And they always have this downwards motion traveling in each location where we discovered the sun quakes. We don't know what was the role of magnetic field. And in some locations, we have for many sun quakes, we have very often white light emission. Not many people reported affection of H-alpha emission, but I will speak about this later. So let's look about magnetic field. So how it is associated with magnetic field. We look at this in paper 2005 for the flare 23rd of July, here hard X-ray emission. We measured the magnetic field variation in each source, and many people then repeated these measurements, including the other papers which were cited, and now it is very popular topic. But what I will say that definitely in the first source, which comes in this top one, that you have kind of step function variation. The magnetic field was one level, then after flare it came to another level, and it was kind of transient decrease which disappeared when the flare stopped. In other, you have direct variation from one level to another. Again, in the third source, you see variation from one level to another with the transient transition. So definitely magnetic field has to play some role. And indeed, later, Hugh Hudson indicated that, and then Welsh, they published the papers connecting these events somehow, and we will look at them a bit later. So these are the flares and sun quakes which are detected before with MDI instrument and never been detected from the ground-based observation. So it was like noise was too bad on the ground-based instruments. But then in 2011, Sarah Matthews, she worked very hard and used the gong instrument for the flare 14th of December 2006. And we managed to detect two sources in there, northern and southern source with nice ridges, which is absolutely remarkable what they've done. So these sources, again, in the location of these sources, in one of those sources when we had a strong transient type variation of magnetic field. Magnetic field was reduced in this source, where later coincide with hard X-ray emission, or we plotted on it. Magnetic field reduced and then returned back, slightly different level, before, to the pre-flare magnitude. So it was for the flare observed with the gong. So what was interesting with this flare? It was that we detected that white light emission was only present in this flare in the location when we had hard X-ray. and it was not present when we didn't have any hard X-ray. So there were few locations when we see white light, and into other locations we didn't see white light at all. So this was reported in the paper Matthews et al. 2011 in ABJ. So it was interesting discovery, which led us to think that obviously white light does occur with sun quakes together, but somehow we don't know what is causing it and why it is located in one location and not in another. So this what summarizes what we see in this 14th December flare, that we observed 4 sun quakes, 2 with the time distance and another 2 with holography, and they coincide with magnetic transients. Some of them are very strong. Those 2 of them coincide with white light and hard X-ray emission, and 2 of them don't show neither white light or hard X-ray emission. So the permanent change of magnetic field seen in the source 1 and in the source 1 and the northern one. Similar step-like changes seen in all the sun quakes. So again, it indicates us that indeed magnetic changes do occur during the sun quakes, but we still do not know what is causing them. So then new cycle came February 15, 2011, where there were 2 sun quakes detected in this flare with both aggression contours and time distance diagrams shown here with the orange lines. What was interesting in this flare, reported by Sergei Zharkov et al. 2011, that he managed first time apply this directional holography result and discovered preferential direction of the waves. For the one of the sources was to the north and another sources was southwest. And plus he discovered the supersonic moment of the waves and in the direction of the velocity due to the acoustic cutoff frequency effect. I will speak about this a little bit later, which is at the moment reporting the observations. So here are aggression power distribution in frequency. So the brightest frequency, the brightest is 2.5, and it is frequency is shown on the y-axis, and the bottom is the time. So you can see that in one of the sources, basically the strongest power happening about between 5 and 6 millihertz. These 2 sources do not show any low frequencies, but if you look at the other 2 source, other source, this was first source, this is the largest second source, it turns out that it shows very strong aggression power at the 3 millihertz frequency. So definitely, again, sometimes the seismic emission which you observe from sun quakes, they are different in frequencies. So they have, here is the distribution of acoustic energy in frequency. So they see that source 1 had higher power from 10 to 28, decreasing with frequency. So the lower the frequency, the higher the power. And obviously, the energy deposited in sunquake can vary from 1 to 10%, depending how strong was the source which delivered these acoustic waves to the interior. So now we move on to some statistical understanding. So we see how different are sunquakes and how different even is energy they deliver in different frequencies. So Bisli and Ionescu, she analyzed and Alina Denis also analyzed that actually the most active, most powerful flare of X class, they are not actually delivering the most powerful sunquakes. Most powerful sunquakes are delivered by M-class flares, strangely enough, which tells you something about transport. So it means that whatever energy is delivered, it has to be spent, less spent on the upper atmosphere and preserved to deliver to the lower atmosphere. So they should not be producing very strong hard X-ray flare, should be M-class. We observe even C-class flare with the sunquake, but not the X-class flare. And you see M-class flare, they have energies 10 to 27, 10 to 28, while X-class flares have 10 to 25, 10 to 26. So basically, again, it tells you that something happening differently, and sunquakes are very important proxy to understand the energy transport from the upper atmospheric level to the bottom. Now we come to the modern era, and we look at the recently published paper, McRae et al. 2018, who investigated 6 September 211 flare. On the left-hand side, their time dependent count rate, white hard X-ray, the power of the flare, magnetic field variation, again, transient type, normalized intensity white light, and aggression power. And on the right-hand side, here the location of this particular sunquake, which has been missed by other people because the disturbance which is produced by this flare was actually very directed. So it was not disturbance for the whole circle like here, but only in this quarter you could pick up some information. And Connor and Sergey managed to gather it and improve the holography technique and discover this sunquake. After we knew where it was located, they basically managed to produce this time distance diagram, which is not the best one, but it is still visible. So this is what they detected in this flare. I will speak, this is the location where the particular sunquake was located in here, and these are contours in different frequencies. What is interesting in here, this is white light core observed with the flare, and this is white light in the red light observation in this core where it was sunquake. The blue is our theoretical curve, which I will speak about it later. So now we move on and say what we managed to gather before we started doing modeling. That, for example, we look by the 2018, look at some 17 flares, we observed themselves, and only 8 had time distance diagrams, and all 17 were detected with holographic techniques at some distance, 120 megameters. Area of the seismic source is small and varies from 1 to 10, 10 to 17 square centimeters. Most X-class flares are acoustically inactive, but it doesn't mean that they don't have these shocks. Probably they produce the ripples which we cannot detect. M-class flares show much more acoustically active acoustic activity, and they're associated with high energetic particle of moderate fluxes or with the hard spectral index, small spectral index, which can reach deeper layers, possibly. The momentum measured from seismic sources, need to come back, varies from 0.1 till 5, 10 to 22 gram per centimeter per second. And they're comparable with those delivered by hydrodynamic shocks caused either electron or proton beams. So what are the mechanisms associated with sunquake, and based on these restrictions which we have? So we started first from the hydrodynamic shocks. So plasma temperature, density, and velocity is governed by hydrodynamic of ambient plasma to injection of electrons or proton beams. So this is what we done with Sasha Kosovichev, then we done with Sergey in 2007, 2015. And it looked like plausible mechanism. We'll look at that. But alternatives were also suggested. Dania et al. 2006 noted that very often when we have hard X-ray ultraviolet emission during sunquakes, we also have white light emission. And she suggested that possibly all this high energy emission, including it produces also contributes to, it produces actually a seismic emission, because they thought it is emission which is seen, that it is not acoustic wave, as far as I understood. Then there was the idea of fast magnetic field changes produced by Hugh Hudson and Fisher et al. That magnetic field changes are they irreversible or transient one, as we reported with Sasha in 1999 and 2001, and then Zharkova et al. In 2005. So this is plausible and obviously related to each other. So definitely magnetic field has to play important, if not the key role in all of it. So indeed, magnetic reconnection sets up Hall flare phenomena while producing energetic particles, and which in turn can produce hydrodynamic or magnetohydrodynamic shocks and produce magnetoacoustic or acoustic waves. But how are these mechanisms are acting? So this is the thing. So how they produce? So you put the particles, they produce the shock, they hit the surface, and that time we thought that the waves are like acoustic waves are produced when the shock hit the surface, or if magnetic Poynting flux hit the surface, or white light emission or higher energy emission somehow hit the surface. So whatever it suggested, this has to be done with these three. There were no other in the view. So what to legalize that, we discovered that not only electron beams produce shock, but proton beams, we needed to do kind of extra job for particle acceleration with Mykola Gordovsky, with Taras Siversky. You know, this paper published in the RESI book, Zharkova et al. 2011. So what we see that we legalized the electron-rich beam compensated by return current precipitate very quickly in one set of loop legs if you have two interacting loops. And the proton beams could precipitate, proton-rich beams can precipitate in other two loop legs, thus legalizing that indeed you can have the foot points with gamma ray emission or foot points with hard X-ray emission, which are separated in time and in space. So, okay. And sometimes they're not fully separated. They can be traveling all together, which involves different effect, ambipolar diffusion, some other which still need to be investigated. So anyway, we have the particle beams which are injected from the top. I'm looking now at the electron beam, which are shown precipitating by the green line. And these electron beams are immediately shown when we solve the Fokker-Planck equation. They form the electric field induced by themselves, and they form the return current formed from the precipitating electrons. So basically, electrons are turning themselves back to the source. And this is called self-induced electric field, which is often observed in the active experiments in the ionosphere. When people try to produce electron beams there, they know that after they send the electron beam from the satellite, they need immediately to charge the satellite with the positive charge, with the negative charge. Otherwise, electrons will come back because of this return current effect. So anyway, what we did, we considered particle precipitation using Fokker-Planck equation. On the top are the authors. Why we needed this? Because we needed to hit the plasma with different beams. So we needed to see whether they are eligible, whether they can hit the plasma and produce the shocks. So this is why we put those beams. And plus, remember that M-class flares produce the strongest some quakes, while X-class flares sometimes do not produce any. So we needed to understand what is different between M and X-class flares from the X-ray emission point of view. So in this case, we look Fokker-Planck equation, we look time-dependent distribution function using the collision, using the effect of return current. And this is the collisional term. And this is the term which includes the pitch angle diffusion, which is now very popular with many guys. And this is the term which shows the variation of magnetic field convergence, which leads to mirroring, particle mirroring. So what is electric field formed? Come back. Electric field is formed by the same particles. So we, at each height, we calculate the particle density and electric field formed by these particles. So after we done this, we solved time-dependent Fokker-Planck equation with Taras-Sieversky in 2009. And what we have discovered, this is the beauty of it, this is the precipitation of electron 12 keV, 50, 100, and 500 keV. So what you can see, so this is the atmospheric depths. This is transition region, 10 to 18. 10 to 12 is chromosphere. 10 to 22 is photosphere. What you can see, that electrons are, the high energy electrons, they reach in the photosphere much quicker, while the lower energy electron only start precipitating in the upper layers. So what is happening, basically, the atmosphere heating starts from the photosphere. This is the heating function at the bottom is heating function. So it starts from the photosphere and then moves to the chromosphere. So what we can see is that electrons with the energy above 100 keV, they all can reach the photosphere. So obviously, how they precipitate and how they emit the energy defines the class of the flare. This is X-class flare. So this becomes now obvious that the more electrons precipitate to the photosphere, the more they can produce something with the sunquakes. But if they all are stuck before the transition region or somewhere in the upper chromosphere, they produce very strong X-class flare, but nothing is left to deposit what is beneath. So this explains what is puzzle in transport can be solved with nice hard X-ray emission. So this we now look at the full Fokker-Planck solution when we continue to inject electrons steadily. So we continue inject, before we inject only 0.10 - 3 seconds, but now we injected, let's say 5 or 10 seconds, and what we discover, that within about 100 milliseconds, we established this nice circuit. Remember this return current? It is not invention. As soon as you get Fokker-Planck, you see that electrons coming down, these electrons coming up. And this circuit exists as long as you keep injecting electrons. Only when you switch off your injection of electrons, the circuit stops. What does it mean? It means that within a second, electrons makes 50 journeys, 50, sometimes 100, sometimes 25. Let's say in average, if it doesn't make only 100 or 50, it means that you need to accelerate 100 less electrons to get emission in hard X-ray, which you observe. This resolves the particle number. So very important put into the transport of high energetic electrons. But and also it explains that obviously the harder is beam, the probably deeper it can penetrate, and the softer is beam, it is established the circuit in the upper layers, so it produces very strong hard X-ray emission, X-class flare, while not depositing much into the lower layers. So this was interesting journey to understand how the energy is transformed, energy of magnetic field during the connection is transformed into the particles, and energy of hard X-ray emission. So this is the electric field formed by, let's say, beam with the flux 10 to 12, constant part in the corona, and then very steeply reducing part in the chromosphere and photosphere. If the beam is weaker, the constant part goes up to the middle chromosphere. So basically the electric beam takes care of itself, establishes the circuit, and allows electrons run up and down and hit the plasma until it is injection is stopped. So here are examples. We published this with Mikola in 2006. We showed the electric field induced by these electrons. Return current electric field is actually much higher than Dreiser electric field. In some occasions, if the beam is strong, so it could act as the additional heating. Plus, two beam instability can easily produce the turbulence, which most of you like. So the turbulence also legalized by the presence of two beams. But the main thing is that what we observe the.
Valentina, for some reason we cannot hear you well now.
Pardon?
Just now I can hear you well. Yeah.
Can you
Please
hear?
continue. Yeah,
Okay.
I can hear now.
Hear?
Yes.
Can you hear me?
Yes.
Okay. Okay. Can I continue? Okay.
Sure. Yeah.
So what we see power law distribution. So there is the softening, the hardening of the spectra towards lower energies. So this is the flare 23rd of July 2003 shown by Gordon Holman. The lower higher energy part has index 6.2, lower 4.8, 6.3, 5.2. And this happens very often, so I skip this bit, bring you to our nice animation we done with Mikola. So it shows that if the beam flux of the beam increases, it will be flattening of lower energy spectra, because of this part of the electrons are returning back. They actually coming back as return current. This is why it's flattening happening. So the higher is flux, the higher return current, the highest flattening. So this is causing soft, hard, soft variations. So basically this helps us to understand why we have why hard X-ray is higher in those pairs when we don't have much of sunquake. But also
Valentina, again we have problem with your microphone.
I don't know what to do.
Now it's fine.
You you keep telling me when I still speak, and I'm trying to keep it straight near me. So anyway, what it said now, why we use, I'm showing it. So when you observe the flare, if you observe the flux is strong, you are not surprised that the spectrum has two power laws because of this effect. But in this case, when we legalize the beams, so we know the beams, we can now move to the hydrodynamic response of the flaring atmosphere, because in order to understand sunquakes transport, we now need to look what is the transport in the atmospheric level or hydrodynamic response 1 of a flaring atmosphere. So I put these equations which we use, which were similar, which Boris Somov used 81, Zharkov and Zharkov 2007, and then with Malcolm et al. 2017, and so on. And after that, so what we basically we do energy equation, ions and electrons, but mostly we concentrated on the electrons one. And what we basically managed to obtain,
5 minutes.
Pardon? 5 minutes?
5 minutes,
no,
yes.
It cannot be 5 minutes. Okay, I will try to finish. So we have temperature distributions, which is top row, but what is most important, this middle row, which shows that we have formation of hydrodynamic shocks. The first one is model beam 10 to 10, the second model 10 to 11, the last model 10 to 12. And you see the form hydrodynamic shocks with the velocity 10 to 11 up to 200 kilometer per second, and the macro velocity of 10 to 12 reaches 400 kilometer per second, and the density of particles is very strong in there. So for this one, we use this interpretation with our paper in Nature Comms. We found the jets which are traveling out in 171 angstroms with air A for the flare 30th of June 2013, and the speed of jets was shown in here exactly as predicted by the simulations. Then we look at the H-alpha emission, and what we found, which was very important and explain why when we see sunquakes, we very rarely see simultaneously H-alpha emission, is that H-alpha emission becomes very much redshifted. So with each second, when the beam comes and forming this shock, you see, we can come back to see that this is the intensity 10 to red line F 10 to 10, green 10 to 11, and blue 10 to 12, H-alpha emission, both cases. And these are which one is this? This is Paschen alpha emission. So what we can see that formation of the sunquake removes actually H-alpha line outside the window of observation between 1.5 angstrom and minus 1.5, because the line is shifted by 3-4 angstroms to the red line, to the red wing. So this is why, because of the strong ionization, we see that. This explains why we don't have H-alpha observations. This is interpretation of H-alpha observation in smaller flare, which we couldn't observe H-alpha on the right-hand side and could reproduce it with the simulation on the left-hand side. And I skip this one to make it quicker. And what become very important, that ionization degree produced by non-thermal particles is very important. So it become, from the ionization which you expect at this depth 10 minus 6, it moves to 0.2, 0.1, and reaches even 0.6 to some very strong beams. So obviously this extra ionization, probably the one, as we shown, Druid and Zharkova, we shown this is the contribution function to Paschen continuum emission with only thermal emission. And this is when you have beam. So you see that white light emission moves to the chromosphere and coincide with the location of hard X-ray, as it was reported Martinez et al. 2012 and later. So this again brings us that we reproduce white light emission with this model, which corresponds pretty well to the observed curve. Why it happening? So what is happening with the sunquake? What is happening? We plot our hydrodynamic model with the height of the quiet sun atmosphere. So far we were looking at the depth in the flaring atmosphere. So now we return back from what we started. The beam was injected pushed whole atmosphere down, and what it does. So this is the atmosphere. I've shown you on this one. On the left-hand side, this is positive heights, and this is underneath, and the quiet underneath of quiet sun photosphere. So what you see, the beam pushes this atmosphere to the deep layers in the solar interior. And what is more important, when you plot the macro velocity, it pushes it. This shock travels with the velocity higher than the speed of sound in this interior. This is the reason why we applied the second hydrodynamic model, which Sergei Zharkov described in Monthly Notice in 2013. So basically, this is the model, how it works. Oops, it doesn't want to show. So what basically it produces, if you look at this, it produces, so you can deposit your shock, not necessarily at the surface. Your shock travels underneath, and depending on the depth where it is deposited, it is different distance where this wave can be reflected from the photosphere. So basically you have lower turning distance where your sound wave travels, because it travels super sound speed, then it travels, and according to the Fermat law, it is reflected from the solar interior, comes back to the surface, and this is this upper turning point when you see the first ripple. So it is possible to calculate the distance in which you see the first ripple from the first one, and the velocity with which these ripples will be propagating on the surface, using either polytrope model of the solar interior or the model of Christian Dalsgaard, which also was used for comparison. And when you look at the simulations, you can discover that if you deposit the shock slightly beneath of the lower of the quiet sun atmosphere, you see that some part of acoustic waves can reach the surface, while other part, because it is deposited at the angle, so this part would reach, and you can see the ripples here and disturbances. Well, in other part, you wouldn't see until probably 25 minutes from it. So this is why the directional holography becomes very useful, because you can pick up information from this part when you have the ripples. If the shock deposited very deeply, the disturbance will be pretty symmetric very quickly, which was shown in this comparison. 3 minutes deposited much deeper in the solar interior, and this you have nice ripples, so you can observe a nice reach. So this basically end of my story. I can say that sun quakes are part of the flaring process and associated with magnetic field reconnection, generation of energetic particles, which generate transit magnetic field, and hydrodynamic response of the atmosphere. So all these guys who produce different mechanism for producing sun quakes, they're all correct. These mechanisms are playing all together. So this is the good news. So we can start working together, exploring different aspects, but they all come together. So high energy particles have dual effect on flaring atmosphere. They heat it via hydrodynamics. At the same time, they produce non-thermal ionization and excitation, producing hydrogen and other emissions, which is very important. We proven this. Malcolm, it works very well for interpretation. Hydrodynamic shocks are deposited beneath the quiet photosphere. And the deeper they deposited, the more symmetric could be the disturbance on the surface. This now explains that the acoustic waves are reflected, so we know at which point you have first bounce, and so you can understand now that not all reflected waves can be picked up with the reach, because they're not strong enough to put the photosphere up above the surface, And this is why we don't see the reach, but you can still see them in holographic images. So the ripple height, distance from impact, and horizontal velocity depended on local speed of the sound in the solar interior and acoustic cutoff frequency, according to Sergei Zharkov, 2013. Thank you very much. Hello?
Thank you, Valentina, for a really very interesting talk. Now we still have some time for questions and comments, so please go ahead and ask a question if you have. First, unmute your microphone. So far, all microphones are muted. I meant to ask one question. Do you have any indication or correlation of sunquakes with so-called cold flares, even weaker than M class, when you do not have a lot of Gauss response in X-ray?
No, we didn't see any sunquakes associated with cold flares. To see sunquake, you have to have very strong deposition of momentum to the under the surface. So if cold flare doesn't produce deposition, then we don't see any disturbances. It is like you know, the superjets. Remember this Concorde? When you see you listen in the terrestrial atmosphere, you hear sound of the plane when it flies before it exceeds the speed of sound in the atmosphere. In the solar interior, to the contrary, the shock has to exceed the speed, then we can see it from the ripples. When it drops below, we can't observe it. It is there, but we can't see it.
Okay, thanks. Any other questions or comments? I see that all microphones are muted, so that means that we do not have any further questions. So thanks, Valentina, for your talk. And next forthcoming talks are listed already at the webinar webpage, so it will continue running on 4-week schedule. So please consult webpage and associated Google Calendar, which you can add to your Google Calendar. Thank you very much, Valentina.
Okay.
Thank you very much, everyone. Bye.
Bye-bye.
Thank you.